So yeah, hi everyone. Welcome back. Today we have My Network, which is another FHE company, and we have Christian and Ashley today from the team. Welcome both of you guys. And yeah, today we'll do a deep dive in the project and just have a FHE focused conversation. Um, Maybe just to start, would you like to introduce yourself, Christian and Ashley?
Ladies first. Go ahead, Ashley.
Okay, hello everyone. So my name's Ashley, and I come from my network, and I'm responsible for the department of R&D. And so basically, I graduated a PhD from a cryptography. So now I'm fully dive in the FHE technology, and this is basically my information.
And my name's Christian. I'm the head of BD and marketing at my network. I've been with the team for almost a year. My background is in sales teams, business development, marketing for tech for a dozen years. I've been in crypto for 3 years. And happy to be here. Thanks for having us, Remy.
Yeah, definitely. So my network has started a while ago, and could you walk us through kind of like the journey of my network? How did it start? And also, so that you guys had a Ethereum protocol fellowship as well. Just walk us through kind of like the early days of my network.
Yeah, I think Ashley can speak to this too, having come on before me, but our three founders were PhDs in computer science and cryptography. So Mason, Dennis, and George. Dennis was on the team that was the first team in the world to hack Tesla. He got to meet Elon for the effort. Really cool story. And then Mason had a deep background in AI, and they all were very, very, very enthusiastic about FHE. And so this, as you know, Remy, very well, this holy grail of cryptography has been a hard nut to crack. It's been around since the late 70s, theoretically. And it wasn't until 2009 that Craig Gentry figured out, hey, this actually can work for sequencing the human genome. So it's very good for processing with really sensitive data. And so the team started putting together some documents and some white papers in, I think it was early fall of 2022, right? And then we started to find some footing and some real practical use cases. So the first product was a data lake, and the concept got pretty viral. It was like, if you could create an FHE data lake where you use zero knowledge proofs for the input and the output, and then allow third-party computation on top of the data, you could add off-chain data with on-chain data. So the initial use case was, imagine taking your credit score from the real world and combining it with all of your DeFi activity in Web3 over the last few years and creating a comprehensive risk profile for underwriting a loan. And so that raised a few eyebrows with a number of projects, DeFi projects and others. And so we were off to the races from them. That was the first real use case of real application of FHE, and it was something that kind of worked around the speed contingency, and it was a ready to go product. So we integrated that with Arweave and with IPFS and BNB Greenfield, these kind of long-term decentralized storage solutions, and it worked out pretty well. And then in terms of the Ethereum fellowship, so Vitalik Buterin has been talking very publicly for the last several years about how Ethereum's got these three big challenges to solve as an ecosystem. And the one that he always names as the forefront is privacy. It's like if Web 2 became Web3 today, all of our groceries, all of our geolocational information, all of our app subscriptions would all be in a public ledger, completely, visible. All someone has to do is figure out, a wallet, tie it to an email address, and they know what you're doing. So that's not realistic. We've got way better privacy in Web 2, albeit centralized, but the privacy standards are better in Web 2. So we really have to figure this out. Privacy, confidentiality, what it is, whatever you want to call it, there has to be an acceptable layer of this if you're going to be interacting with the web as much as we all do. So our stealth address protocol, which Ashley had a hand in, and she can speak to better than I am, but we used FHE to generate the private key pair in stealth address protocols. So it's a FHE DKSAP dual key stealth address protocol. And what that does is it basically masks sender receiver wallet information, like EOA information, as well as token type and volume. And so that was a really big solution, and that caught Vitalik's eye. We applied for an Ethereum fellowship, won a fellowship, won a grant to basically develop this technology in the Ethereum EVM ecosystem. Ashely, if you'd like to make a couple of comments about that as well, since you were pretty pivotal in that.
Okay, so it's the FHE based dual key source address protocol. It's actually motivated by a challenge of the privacy. So you know that where address is public key, it's driven from the public key, and if other people knows our address, they can trace the record. Basically, it will reveal a lot of information about the person. So it brings a lot of privacy challenges. So our motivation is that we can preserve the identity of the recipient. So nobody knows that where your tokens goes somewhere, and this information is totally hidden by this dual key stealth address protocol. However, actually the dual key stealth address protocol, it's not fresh. It's not newly proposed. It was highlighted by Vitalik like last year in the beginning of 2023. But he mentioned a lot of challenges that this dual key stealth address protocol facing. One of the problem is about key management and how we can manage the keys. It's a huge challenge. By the way, you have to consider the quantum cryptography problem. You know that quantum is actually approaching. So based on these motivations, we somehow improve this protocol based on the FHE technology. In this case, nobody can, first of all, it's resistant, it's quantum computing resistant. And the second, we use this FHE key management to encrypt the the recipient address. And in this way that this transfer, it can be privacy preserving. So this is basically the idea or the story behind this protocol.
Yeah, very cool. Yeah, you guys were definitely one of the earlier projects diving into this direction and then leveraging FHE to solve some of these existing problems with a very different angle. And yeah, stealth addresses have been around, discussed for some time. There are a few proposals. There's even a standard called ERC 5564. Some of them use also very different solutions, right? A lot of them are different elliptic curves using like SegP 256 K1 or R1. I guess like you mentioned earlier, I think FHE here is a fairly different solution, which benefits from the post-quantum security, basically. I guess beyond the post-quantum security, let's dive a little bit deeper into what other benefits do you see doing stealth address using FHE compared to existing solutions?
Mm-hmm. So I think the main benefit it's about the key management, and also previously their protocol have the risk of the key, so it might somehow leakage your private keys. So if your private key will be leaked, it brings a lot of security problems. Somehow in FHE based dual key stealth address protocol, now the user will have two key pairs. One is their private key, and another one is FHE key pairs. We will use the FHE based key pairs to encrypt all the messages. And in this case, these two key pairs will be separated. So even your FHE based key pair might have some problems, you're afraid of the storage, you are afraid it might be leaked after some while of use, it will not influence any to your EU address key like private keys. So somehow we maintain the key management. And secondly, I think it's very important that stealth address is one-time generated. So if you have to use stealth address, you have to generate a key each time. So this is very time consuming and the storage consuming, especially for encryption. But in FHE, we only need to use the FHE key pair one time. So we don't need to generate the key pairs from the user side every time. We just use the ephemeral keys each time when we need to encrypt it. And that one, it's very easy to generate, and we will just abandon it after the stealth address is generated. These are two main advantages when we use FHE. We separate the key pairs, and we also preserve the privacy of the key pairs.
That's a really good point. Yeah, go ahead.
I was going to accentuate the point she made, which is that one of the key pairs is stored locally as well. So compared to regular key pair management, it's actually a lot more convenient to the user.
Yeah, so just to make sure I understand correctly, in regular stealth addresses, you have to generate a new key pair for every new transaction, right? Because you can always sort of, recompute and guess what the stealth address is by using the same key, right? But FHE, because every time you generate a ciphertext with FHE, there's this random factor that changes the ciphertext. That's why you can reuse kind of like the same key or the same address without having to go through the same process for the typical stealth address. Is that correct?
Yeah, so there are the sender and the recipient. So every time this recipient, he will maintain the key pairs of the FHE. And the sender just need to, so assume that I need to send a Remy, or I also need to send the Christian. So each time as a sender, I will generate a random keys. But for Christian and Remy, when you receive my tokens, you will preserve these same key pairs. So you don't need to change. As a recipient, you don't need to change anything. But as a sender, I will adjust these key pairs, temporary key pairs every time. But these key pairs will not influence anything because once the stealth address is generated, I will just abandon it. It's not useful for me anymore. And based on this, the privacy is preserved. You as a recipient.
Yeah, and the sender doesn't need to do anything themselves. It's done for them. Yeah, so.
Got it. Could you maybe walk us through the flow, right? So if Alice wants to send some money to Bob, what would this entire flow look like?
Christian, do you want me to do it, or you want to introduce it?
Yeah, generally speaking, yeah, you can go ahead. You just kind of touched on it. It's like, Alice is sending to Bob. Alice is sending to a stealth address first. The stealth address generates the key pair. So, yeah, that's the simple architecture of it. And then Ashely can dive into the details.
Mm-hmm. Actually, this protocol is not easy for the person who don't have any background of cryptography because it will attach the key pairs, the generations, and the magic thing that how another party he can know the stealth address without any other information, right? So this is the magic of the stealth address. So the floor, as far as I still remember, because I wrote the white paper, but it was a long time before. Yeah. So the floor works like that. So for Alice as a sender, Bob as a recipient. So Bob, he will have two key pairs. One is the FHE key pair, and another one is, as usual, the EOA key pairs. And for the Alice as a sender, he only have one key pair, but he will generate an ephemeral key each time. So this is the key pair setting, and the process is that at the beginning, the Bob as a recipient, he will share his information of the public key to the both of the public key to the Alice. And Alice, he will encrypt the temporary key by the public key of the FHE. And this will turn to a ciphertext. And then he will also encrypt his ephemeral key, the ephemeral public key based on the same public key, FHE public key. So in this way, the Alice, he will get two ciphertexts. And the homomorphism, the additional homomorphism of FHE. So Alice, he can add these two ciphertexts together. And in this case, he didn't touch any related information with the private keys. So once he have this addition of the ciphertext, he will return this ciphertext to the Bob. And Bob, he can decrypt it. He can decrypt this ciphertext by the secret key of the FHE because Alice, he used a public key to do the encryption. And in this way, in the terms that the Bob, he can only decrypt this ciphertext with the FHE secret keys. So he got the secret keys, he got these ciphertext, and the addition actually is a plain text of the Bob's public key plus Alice's ephemeral key. And this is the secret key that we generate this stealth address. And Alice, actually, he knows the ephemeral key and he also knows the public key. So somehow, without touching any private keys, they can negotiate on a stealth address. So this is basically the protocol.
Very, very cool. So essentially there is a way for Alice using, Bob's public key, EOA public key. So Alice knows that they want to send money to Bob to generate this stealth address, which I assume it's also a EOA, right? Because it has a private key linked to it. And then Bob can basically derive this private key of this stealth address EOA and then claim it, right?
Yes.
Cool.
Totally.
I'm kind of curious, if Bob were to claim, that money, right?
Mm-hmm.
How does he solve the gas fee problem, right? Because he will have to send some gas fee to this new EOA stealth address and claim it, right? So I guess what are some workarounds around this problem?
Actually, from the protocol itself, we don't need to touch the gas fee so far because it's only a key generation or it's only a stealth address generation. However, it does bring down gas fee problems because the FHE, it has a higher computation cost or the storage cost because you have to work on the ciphertext. But according to our development, their feedback, this gas fee is quite considerate. It's still manageable as usual. So this is what I got from the development phase.
Got it. I guess I was more thinking about from how do you prevent information leakage to claim? For example, in the older stealth addresses, I've seen people think about account abstraction. So the idea is if I'm Bob, I want to claim this money, I need to seed in some gas fee, right? But with account abstraction, you can go around this problem potentially. So okay. I was wondering if you guys have something around this as well to preserve privacy throughout this entire flow.
I got your point. I think the best thing of this protocol is that you don't need to prove that you have the identity because you are the only person who has the secret keys. And secret keys is actually an identity. And this is your private information. So other person without these secret keys, they can not even decrypt the ciphertext and they cannot generate the stealth address. It's just like random information for them. And only the person who owns the FHE secret keys, he can decrypt the ciphertext. And this is the only way he can prove he is the owner of the stealth address and he can open this wallet.
Okay, got it. And that proof happens on chain. So I assume for your self address, you have deployed a set of smart contracts, right? To verify or to basically prove that you own this address.
Yeah. So it's written on the smart contract.
Got it. I'm kind of curious, what are some interesting use cases of stealth addresses that you've seen today? If you're working with any, partners, enterprises, I'm kind of curious to know, why are they interested in this solution?
Yeah, our first customer was Chainlink, and it was for the CCIP bridge. So we learned a lot through that partnership. We learned a couple of things with Chainlink. Chainlink is working, as you know, with TradFi and with traditional institutions as much or more than any other system or network in Web3. And so we got some really valuable feedback from their capital markets teams, which are working with some of these big banks. And there were two things. One is that ZK is problematic from a traditional regulatory viewpoint. The reason for that is that whoever's running the ZK sees the raw data, right? So if you're running the ZK, you do see the raw data. So whoever your ZK service provider is going to see that. So that's kind of like a centralization point. Regulators are like, well, there's still some trust assumptions here. And so the benefit of FHE obviously is that it's untraceable, but it is verifiable, right? This is on-chain computation, and you can look at metadata or the batches, and you can determine bad actors. And then the other issue that they brought to us was that Chainlink uses a decentralized Oracle network, right, to verify transactions. But for every transaction that's done in Web3 or Web2, there's a message that has to go out first. It's called the intent layer, right? So if Remy, if you're at JP Morgan, you're sending me JP Morgan coin, you're converting it into Ethereum, there's a message that goes out on the DONs first to initiate that transaction. Well, if that message isn't encrypted, then the DONs see the message. And if there is a bad actor there, they can front run the transaction. right? They can make their own trade. They can take advantage of this large transaction that's about to happen, whether it's in price or whatever. So as secure as the decentralized Oracle network was, this was a problem for the banks that are trying to satisfy regulators. So our stealth address protocol obviously encrypted that messaging layer. So it's kind of like a Web3 version of Swift, which is the interbank messaging system. You know, Swift is used by, I think, like 180 countries around the world. It's they oversee trillions of dollars of value every single year in transactions. And so our goal is to kind of be a Web3 version of Swift. So if we can encrypt the message as well, then we don't have to worry about the Don seeing or not seeing it. They can still run compute on top of it without actually seeing the underlying data, and there's no risk of front running the trade. So that was kind of our first partner, and then Chainlink made us channel partners for that solution. So that was a big one. And then you can basically copy and paste that format for any bridge. And bridges are one of the weakest ports of infrastructure in all of Web3. It's where a lot of bad actors tend to attack. And there's some really cool solutions coming up, to get over that problem, like Wormhole and Connect. And so we do have solutions with them as well. But this is a weak point in the Web3 infrastructure that I think this solves really well. And Chainlink was our first kind of product market fit there.
Yeah, very cool. I think the problem that you mentioned is essentially you leaking information about your intent, especially if you're to move large amounts of money, and then people could front run you, things like that. And I think definitely masking the metadata or the intent is actually definitely super helpful, super useful. I guess on the bridging side, I think this is an interesting topic as well. The idea is that, for a, FHE based blockchain like Inco or Phoenix, if you want to move money, let's say from Ethereum or a different transparent blockchain to one of these, confidential compute blockchains, then people could already see that you're moving, let's say, $1,000 to this address, right? On Inco or Phoenix. Maybe tell us a little bit more about how stealth addresses could potentially solve this problem.
Cross bridges?
Yeah, for the cross-chain bridging use case.
Yeah, it's a similar architecture to the one that Ashely described, right? So, like for Phoenix and Inco, obviously all on-chain assets will have the benefit of FHE encryption. But what about assets coming in from Avalanche, coming in from Ethereum, coming in from Polygon? If you want to actually have the same encryption there as well, so we kind of are a layer that lives on top of the bridge. They can execute the transaction that Ashely was describing before using stealth address, so that at least going into these private chains, you also have this level of quantum security and confidentiality.
Yeah, I guess it kind of sorts of breaks the link. Like if I'm Alice, I have the same EOA on both Ethereum and Inco. If I do the traditional bridging, then people can follow exactly the amounts I'm transferring to Inco, even if it's, let's say, wrapped down the line into an encrypted balance, people can still sort of guess how much money you have, right? But I guess with the stealth address, you could break that linkage, and then Alice can send to a different EOA address and then claim it, I guess, from a different address, right? Which will essentially act as the confidentiality layer.
Correct. Yeah, that's a really good point. Yeah, Ashely, if you have thoughts on that to expand, that's a good point. Because I think what you're getting at there is the idea that you could still see you'd still be able to track. You could see the difference in volume, or I guess in the whole ledger is public, so you could still kind of track this even if you're using a stealth address. So how does FHE mask that, right, from a metadata perspective? I don't know if I have that right, but I think I understand I think you're making a point that I'm not articulating well, but it's been asked before.
But yeah, I think we're on the same page here. The idea is that stealth address is definitely an interesting way to break that linkage. And so the idea is if you want to use Inco, let's say as your banking layer, but if you're transferring, let's say, $10,000 from Ethereum to Inco, people already know that you have $10,000. So even if it's encrypted on Inco, it's people can already guess that. But with stealth address, I think if you break that linkage, then people would not necessarily be able to infer how much money you have. Super interesting. I guess maybe to dive into MindLake that you mentioned earlier, I think it's a very interesting product. to have a sort of a data lake dedicated to FHE. I guess like what are some, I think you mentioned a few use cases, but are there any specific use cases that you guys are most excited about for that specific product?
Yeah, MindLake has become like an ancillary product to some of our other products. So it's like in the CCIP bridge case, the data lake is used there as well as SAP. It's like they kind of work in tandem, right? Because it's for all data. So messaging data, transaction history, identifying data. So it's kind of like it's becoming like a background product that we just kind of use in achieving some of the other product realizations. So it's a necessary piece. In terms of being, to be very realistic, in terms of it being like a standalone product that can really scale by itself, there does need to be there needs to be an uptick, an acceleration in decentralized storage. So the issue right now, like especially if you look toward AI, there are projects like Grass, which is a really hot project that's basically just doing data scraping to feed AI models in the Avalanche ecosystem. And what they'll tell you is that there's still this problem with decentralized storage, which is TPS. It's still too slow. So that decentralized storage solutions have to increase a little bit. And actually, it looks like Arweave's AO, they're doing something there. We're diving into the docs now to figure out if they're solving that problem. It looks like they're trying to. But once that problem is achieved, we built a data pack into those decentralized storage solutions, IPFS, Greenfield, and Arweave. And so when they get that speed picked up, I think this will be a much more scalable product just by itself. But right now we're using it kind of in an ancillary sense for MindSAP, the FHE DK SAP. That's the primary use case.
Okay, got it. So you're using your own data storage solution right now, but you're exploring more of a decentralized, I guess, IPFS based solution.
The data lake is meant for hot storage, and then we partnered with those decentralized storage solutions for cold storage, but there's still a speed issue. Yeah.
Can smart contracts interact with this data lake?
Yes. So the data lake has an SDK, and Ashely, I might call on you to speak to a little bit. What are the most up to date smart contract interactions with MindLake, if you're aware of them? Ashely?
Oh, sorry. I was thinking. Actually, MindLake, it's our first product. And during this, so from the first doc until so far, we are like fresh in our mind and how it can be used. And to be honest, we are the first project we are thinking how we can use the storage in ciphertext, so which is FHE storage. But it's difficult, and it's somehow very difficult to make it or the storage on ciphertext. That's a drawback of FHE. So somehow we make the SQL, which is a data lake tool. So we will use SQL query to encrypt all our ciphertext and stored in this data lake. And now our focus that when we are working on the DK, so still address protocol. Also on the right now we have another product, and how we can store them. It's a question. Do we need to use some other project solutions, or how we can integrate them? So now our solution is that we will put all this sensitive data in our data lake project, in the mind lake. So when we are calculating this sensitive information, or when we have to put a place to store the data, and MindLake is our choice. So which means that actually my network, we are using our own storage solution, which is FHE based storage. So this is a story behind it, and it's only a storage solution. It doesn't related to any other more functions, and somehow, as Christian mentioned, now it's our backup. So when we find other products that we have to make use of it, we will turn to our data lake.
Got it. And I guess the expectation is that in the future, you will connect this data to specific blockchains, right? Be able to consume it and interact with it. That's still a work in progress.
Yeah, it'll function kind of like an app chain, as I understand it, right, Ashely? So it'll be like an internal rollup that we use in that sense.
Got it. And then you're thinking of some kind of like bridging external bridging, or maybe something similar to Celestia with some kind of like quantum gravity bridge, something like that?
I think that for this data lake, we are not somehow extending a lot, because now everything is on the off-chain computation, and we will use roll-up to make it possible to integrate it. This is what we discussed. But for other like functionalities, it's quite difficult to implement. This is a challenge we are facing. And for the quantum stuff, is that FHE is naturally can prevent quantum computing, which means that it's quantum resistance. So no matter in the future when the quantum is coming, we can already prevent it. This is the nature of FHE technology. We are introducing the learning with error, and this is definitely enough for the quantum resistance.
Got it. Cool. Yeah, it sounds like this is still an evolving product, and then this very excited to see how this will turn into down the line. And I guess like the third product that you are working on, which I think is super interesting, called MindLayer. Could you maybe quickly introduce what the product is about?
Yeah, so we have this FHE restaking rollup, and it has a couple of features about it that don't seem connected. But a couple of things. I think, one is that we have a strong AI background, as we said on the team. The team's kind of in that, comes from the Web2 AI community and then transitioned to Web3 AI community. So we've really been looking to this AI space for the last year. Originally what we had done, we had made a product in the fall called MindX, and it was a way to encrypt all of your prompting and chat history when you interacted with ChatGPT. Because privacy was an issue, we foresaw the fact that people were using ChatGPT to do work. So they were potentially giving sensitive IP from their company over to ChatGPT. So we made this app that, made a call to the API, and it allowed people to encrypt all of their prompt and history data and store it locally. So you could store it in ciphertext, and it was really cool. Like you could click a button and see the plain text, click a button back, see the ciphertext. You didn't have to decrypt it if you didn't want. So that was kind of a cool, tested out product, and we had some good iterations with it. But ultimately, for that's a tall order to get to a place where like you have enough demand that you can actually force a company like OpenAI to be running FHE computation, because everybody wants to encrypt and store their data, right? So it was a fun thing, but not practical in the long term. But we kept kind of looking at it, and so what we saw with BitTensor was this really cool approach, which I'm sure you're familiar with, Remy, is the proof of intelligence. And it's kind of like this novel consensus mechanism that's a little bit better suited for AI computation than for basically DeFi computation, which is the main kind of computation that you're doing in Web3. It's like all, asset transactions and transfers. And the reason for that is because proof of stake consensus mechanisms are deterministic. And proof of intelligence is probabilistic, which means it allows for more granular variations in predictions and outputs. So it's better suited for AI computation, because in AI computation, you might have a bunch of validators come up, produce values that are really similar to each other, but not exactly the same. Whereas that's not as likely in standard Web3 transactions. And so we thought this was a really cool idea. It's a great kind of system. And so we're using that a little bit. We're kind of borrowing that. And then what we found out was that in AI, there's also this other problem, which we learned from the BitTensor subnets, which is that BitTensor itself does not solve for the copy problem. In other words, if you're a validator in a BitTensor subnet, you can just copy the output from other validators, and you can achieve the same solution. You can reduce your own compute and still share in the rewards. So this is a security issue, right? Because now you can get like this consensus around the wrong outputs. And we think this hasn't become a problem yet in BitTensor, because a lot of the BitTensor subnets really aren't doing anything real world. Like they don't have, it's like some gaming stuff. It's like there's not a lot of like real world use cases yet. It's just they've created this really interesting framework that people are excited about. But as the AI use cases become more real world and more necessary and more relied upon for accurate information, accurate consensus, this is going to be a problem. So every subnet has started to attack this on their own in their own architecture, where they have to actually protect their predictions. We basically have used FHE to encrypt the AI prediction. It's kind of like think of it as like secret voting. So like kind of like in a DAO where if everybody votes, but you can actually hide the vote and you can see at the end because the voting term might happen over a long period of time. So when the voting term is over, then everybody's predictions are entered into the network and they're all encrypted so other validators can't copy you. So this seemed to be like a really important solution in the AI space that only a few people are really thinking about at the moment, at least that we've seen. And so we kind of take that POI, we add like an FHE to it in terms of encrypting the output. And the same kind of encryption, encrypting the prediction works also in a restaking sense. And this is where it gets a little bit, we're still figuring out how to explain this clearly to people because we've got all the diagrams and we've got this running on testnet, but we're just honing in on the message here. So it's that when you look at the restaking ecosystem, right now with EigenLayer, it's $100 billion of value. They haven't launched their token yet. I'm sure it's going to go up more than that. And this is validated on roughly 200 nodes. That's a lot of value to be secured with 200 nodes, right? So as restaking projects are, borrowing these restaking tokens to secure their new chains, there is the same problem of, well, we need decentralization. We need more validators, but we also need we need this, instead of having a few validators, we need more validators. And so adding FHE again to encrypting the predictions and the outputs actually gives you security up front so that you don't have to trust a handful of validators as much. It's kind of like what EigenLayer is providing with this restaking service is kind of like what every new chain has to go through. So every new L2, when they launch a chain, it's like in the beginning, they'll have 30 validators. A lot of those validators are trusted friends, people that they know aren't going to be bad actors. And then as the market cap and the token pool goes up, they hope to decentralize over time. Use cases go up and market cap goes up. So you attract developers, you attract users, and that encourages people to run their own nodes and contribute to the system. So it's a slow path to decentralization. The trust for validators early on now can be reduced because you're actually encrypting again the output. So you're encrypting the validator nodes contribution to the system. So now you don't have to trust them as much because you've got this extra encryption layer with FHE. So it helps achieve decentralization faster. So for FHE restaking projects, it's a similar solution that we add in terms of this FHE piece as it is to the POI, the AI focused projects. It's very similar, but we do kind of have these two different markets that we're trying to build this product into. So let me know how I did there, if that makes sense.
Yeah, no, definitely. I think super interesting. I think there's a lot to dive deeper into. If I were to summarize everything you described, I think it boils down to the question of like, if we can prevent validators from copying each other's work, then there will be additional security and also guarantee, right? I think you mentioned in AI, the results will be slightly similar, right? Because there is some slight variation in the end result when people train models, right? But if they copy each other, then, then it kind of ruins the model, right? The assumption is everyone should be doing their own work. Same with proof of work or even tenement consensus, right? There is a voting period where people have to agree or disagree with kind of like the block producer, right? But if people are being lazy and not recomputing these things themselves and just blindly copying someone else's answer, then yeah, I think definitely there will be security risk. And I think when you mentioned like with FHE, it sounds like, yeah, you could sort of hide the end result of everyone's work, but still be able to somehow verify and compare. And maybe just from a voting perspective, just cast a vote to agree or disagree, or even verify across themselves the values, right? They're too different from each other. Did I summarize correctly? Okay.
Exactly. Perfect.
Now, I guess I saw that there are maybe some LSTs or LRTs called AI ETH and Mine ETH. Maybe if you could share more information about what they are in your restaking solution.
Yeah, so we will have our own so we'll have our token mine token, and then we'll have a restaking token, which will be mined ETH. So far, I don't know if there's the need for AI. So I don't that might have been an early draft. I might be mistaken about that. I'll have to ask Mason. But yeah, the idea is that we'll also have our own restaking token. And again, we'll have this internal kind of roll-up chain that has some of the other FHE products built into it, like MineLake, that we'll use for this as well. And so, really what we're trying to do there is bring restaking tokens, like a restaking marketplace token, to AI projects. So AI projects basically can add security to their token by using, easy ETH or staked ETH, for example. Using EigenLayer's model, we're kind of like an EigenLayer extension into AI specifically, because we bring the POI consensus mechanism, and we bring the FHE, which is better for AI computation. So that's the goal there, is to bring this, like staked token marketplace to AI builders. We're working with IONET and AIOZ, and we're starting with hopefully with a costume and things like that.
Okay, very cool. Maybe now, just to talk more about kind of like sort of what are some existing limitations that you see, for some of your products, and how you think they will be solved over time.
Yeah, so we're like you guys. We want to find the places that FHE is most applicable now. Obviously, as you're well aware of, there's this hardware acceleration contingency for hardcore AI compute, right? So we're probably still a few years away from that, 3, 4, 5, who knows? So we can't use FHE for everything. We're just trying to be snipers and apply it to places where either speed is not necessarily an issue right now, because you don't have to have, high TPS or real-time data second to second or nanosecond to nanosecond. And so there are still places in the tech stack where those opportunities exist, and that's why we've applied them. If to get to an end-to-end encrypted web, this vision of HTTPZ, we still just have the hardware contingency problem, right? The hardware acceleration problem, that will be a few years to figure out. And then Ashely obviously can speak a lot better to that than I can. She's on the cutting edge of research.
Okay, so for the limitation of the FHE, actually, so first of all, for the POI, this protocol, this project is very interesting and exciting, because we somehow change the way of the consensus in AI. Like traditionally, proof of work or proof of stake, it's more like a traditional way working to prove something. But it's very difficult when we work in the AI, because it's another scenario and we have different information. So now we come to the POI and proof of intelligence. But how we can preserve the privacy of the model's weights or the user's input. So that's why we introduced FHE. And the magic thing is that when we introduce the FHE, it didn't increase the computation cost or additional ciphertext to this computation, because we somehow lighted in the way that when we reach a consensus, so we do not apply directly to the data itself or to the result. So we work through this FHE solution during the consensus. That's why this solution is very interesting in AI. And actually, for the project itself, I didn't see a lot of drawbacks of the limitations of the FHE implemented. However, in other scenarios on other projects, so FHE, the main problem is how we can make it faster and also the speed. But right now, for example, we are trying to implement the FHE in LLM. It's like to make it distributed or even to make it private preserving LLM, but it's impossible because it's too heavy in computation. So somehow we have to find a way to accelerate it. So how to accelerate FHE computation? I think it's a big challenge, and it's also very interesting for us to find solution. And today, also, I just talked with Fair Math. It's another Web3 companies working in the FHE. And we are thinking this is a challenge for all of the person working in the FHE domain.
Yeah, LLMs, definitely. That's like the final boss, right? LLMs.
Yeah. That would be the dream. Run ChatGPT over FHE so people can tell what you're asking, right?
Yeah, but we did some tests and we found that it's it might be possible to do it. So the problem is that we have to find the correct technology to make it distributed and to light the model. So that's our target we are working on. You know, my network is always focusing on the recent research. So to make FHE in LLM, it's our dream.
There's a chance like by the end of the year, they're even open to this with all the litigation that's going their way between the New York Times suing them and the state of California. They've got massive class action lawsuits going after OpenAI to say, hey, how did you train those models? Did you use our data? Because it looks like you used our data. Like Wall Street Journal, New York Times are saying, like, if you used our data to train your models, A, we should have consented to that, and B, we probably are owed, some recourse there. There's some damages. So who knows? I mean, they're an $80 billion company right now. They're making a ton of money, but at the end of this year, if there's government pressure, if there's good demand from the market for some more privacy over these things, if enough businesses are saying, hey, my employees are handing over sensitive IP, there might be enough pressure that they would even, be looking into something like this. And of course, there are FHE centralized departments at like Intel and Google and Microsoft, and that's probably an option they would lean toward. But who knows the way the narrative will look by the end of the year. I don't know if Remy, you saw the Stable Diffusion founder step down from Stable Diffusion last week, Imad Mostak.
Oh, wow.
And
I didn't see that.
Did this.
Wow.
He's doing a little bit of a, like a media circuit tour, similar to how Jeffrey Hinton did last year, where he's saying, look, centralized AI doesn't work. It's really, really bad. It's what they're saying is, what these centralized AI operators are saying is like, look, we already have all your data. We've got most of the web data that exists. The future that we're building probably is going to infringe upon civil liberties. It's probably going to it could very potentially create AI that does real damage to humans. And so he's working with Render. He's completely defected into Web3 now solutions, and he's talking with Web3 operators. So, it looks like this paradigm might be shifting. And so if we have enough support and I think need from the market, and if you've got some early, some cutting edge researchers like Ashely working on FHE for LLMs, who knows, by the end of the year, the narrative might totally change. We might be looking at real FHE LLM solutions.
Yeah, I think the benefit of FHE for AI machine learning is pretty clear. It's more of a question one. I think legislations will probably accelerate this trend.
Right.
And then back to what you guys were saying earlier, I think it's important to sequence the use cases based on what's practical today. And I think based on what you said, you're not doing FHE ML training because it is quite difficult for more complex models, but you are applying FHE on the consensus level, which is a little bit more practical and doable today, which I think makes a lot of sense. I guess maybe, what's next for my network? Could you maybe share a bit more about your roadmap? Anything exciting that people should pay attention to?
Yeah, so we've brought the products we've discussed to market right now, and then partnerships is key. And getting the staked token providers on our side, staked tokens in EtherFi and Lorenzo, Babylon. We like working in the Bitcoin ecosystem as soon as they're ready, which looks like it'll be soon. And then I think the AI solutions are really, really interesting. So we're bringing this AI solution, this proof of consensus for restaking roll up. Like I said, to AIOZ and IONET, we'll have some new announcements, I think, over the next few weeks with other big leaders in the AI space. And so we're excited about those. And so, decentralized compute, decentralized GPUs, that's where we're spending a lot of our time.
Yeah, very cool. I guess, is there anything that, people can try out today, play around, and then, what's roughly your timeline for a testnet or mainnet?
Yeah, I think so. You can go on. We're having Galaxy campaigns, I think, every couple of weeks now. I think we're in our 4th or 5th campaign. So you can definitely go to our testnet. You can use stealth address protocol to transfer assets. You can try out the bridge, just get a feel for how that works, and like using FHE stealth address, which is kind of fun. We have a new one coming out next week, I believe. So we'll launch that on our Twitter, mynetwork_XYZ. And then mynetwork.xyz on the website is where we keep all the updates as well. You can see our stats. Our testnet's been up for a few months. I think we're approaching 3 million transactions and like 700,000 users. So the community's been really supportive, and so far they're enjoying the ride.
Very cool. And I guess, anything else you guys wanted to share?
We're really excited about our Inco partnership. Very excited to be working with you guys. There's incredible talent in this space right now. We're just Inco and Phoenix are just two great projects, and we really appreciate your partnership and your support, and we will do the same for you every chance we get.
Yeah, definitely. I think specifically on the stealth address, I think it is a fairly important component, especially on the bridging side, if we want to preserve, full privacy. Quite excited about some of the products that you guys have come out with. Maybe my last question is, if you have a wish list, right? What will be like one wish that you hope to see by the end of the year? Like, what will be one thing in the crypto space that you'd like to see happening?
We nailed it from FHE, FHE LLMs.
FHE?
It's not practical.
FHE LLMs.
I mean, yeah, 100%. That'd be my wish. Ashely, what about you?
It's very hard to say, but for me, maybe I really want to make the FHE LLM to be realized.
Yeah. Same.
Yeah, that would be great. That would be big for sure. Great. Well, thank you both for coming today. I think we covered quite a bit. Thank you so much.
Thanks, Remy.
Thank you. Bye.